So, Friday we looked at the graph of an exponential function, what it looked like. We talked about the fact that an exponential function is in the form y equals c to the power x. Now, we're actually going to add to that a little bit. On the formula sheet, it has this as the general form of an exponential function. Okay? So for now, we're not going to worry about the t and the p part. We could put an x in there for that. Okay? But what we're adding here is a coefficient. Right? So that's going to be tied into our transformation stuff that we've been learning about. So you can see here the graph of the form f at x equals a times c to the power b bracket x minus h plus k is obtained by applying transformations to the graph of the base function y equals c to the x, where c is greater than 0. So we saw two different types on Friday. Where c was greater than 1, we had an increasing function. When c is less than 1, we had a decreasing function. But those parameters a, b, h, and k do the same thing to exponential functions as they do to all the other types of functions that we looked at, where a causes a vertical stretch about the x-axis by a factor of the absolute value of a. And the reason the absolute value of a is used there is the stretch factor is never negative. If a is negative, remember that causes a reflection about the x-axis. So as a mapping notation, x comma y maps into x comma ay, because all the y values are multiplied by a. So you can see two examples there. One where a is 4, so it's vertically stretched by a factor of 4 compared to 3 to the x. The second one where a is negative 2, that'll vertically stretch by 2 and reflect over the x-axis. The b value causes a horizontal stretch. Remember, the stretch is about the y-axis, and the stretch factor is 1 over the absolute value of b. And when b is less than 0, the graph would reflect about the y-axis. So these two graphs are a transformation of y equals 2 to the x. So this first one is y equals 2 to the power 3x. So that is a horizontal stretch by a factor of a third. So all the x values get multiplied by 1/3. And then the second one is y equals 2 to the power negative 0.5x. So two things happen there. It's going to be horizontally stretched by 2, the reciprocal of b. The b value is a half, reciprocal being 2, as well as reflected over the y-axis. So as a mapping notation, x comma y maps into x over b comma y. Right? K causes a vertical translation up or down. So comparing to y equals 4 to the x, this is 4 to the x plus 2. It shifts up 2 units. Remember, those base graphs have the x-axis as a horizontal asymptote. So when a graph shifts up, everything does, including the asymptote. And then the second one is 4 to the x minus 3, so it shifts down 3 units. And then the last one, horizontal translation, left or right. So that is our h value. Remember, h is hooked directly onto the x. Whatever happens to the x happens to the x minus h. In this case, it's part of the exponent on the base. Okay, so this is nothing new. We have been doing this since the start of the course. Didn't talk about it as much in trig. A little bit we did, but definitely not as much. But the same things apply to logarithmic functions, exponential functions, and next chapter is logarithmic functions. We'll be doing the same transformations to the graphs of logarithmic functions as well. So if we have the base function 3 to the x, for each transform function, we'll state the parameters, describe the corresponding transformations, and then we'll create a table of values to show what happens to the given points under each transformation, and then we'll sketch a graph. Well, we'll start with our base graph, y equals 3 to the x. So you can see we've got our table of values there for that equation. The first point is negative 1 comma 1/3. The next point is 0, 1. The next point is 1, 3. Then 2, 9. And then 3, 27. So here's the graph of y equals 3 to the power x. The x-axis is an asymptote. We saw this Friday when we looked at the table of values for an exponential function. No matter how small x gets, y is always positive. The smaller x get, the closer y will get to being a value of 0, but it'll never get there. It's always positive. So, for our new graph, we have an a value of positive 3. So that's going to cause a vertical stretch. And that vertical stretch is about the x-axis. The reason being is that you take the distance that each original point is from the x-axis. That's what the y component tells you. It tells you how far above or below the x-axis you are. That distance is being multiplied by your a value, the absolute value of a. It's being stretched about the x-axis by a factor of 2, the absolute value of a. Then, remember, this is a transformation of y equals 3 to the x, so the base 3 is already there. The only other change is that x is replaced with x minus 4, so that is our h value. Our h value, remember, is the opposite of what it appears to be, because the general equation is x minus h. So to get x minus 4, h is just replaced with positive 4, which means the graph is going to shift 4 units right. So one of the best ways to sketch your new graph is to start with your base points and apply each transformation to those points. So the first thing we have again is an a value of 2. That's going to cause a vertical stretch by a factor of 2 about the x-axis. All the y values are multiplied by 2. Each y value is multiplied by 2. So you see in this case, the y-intercept is changing. Instead of 0, 1, it's going to be 0, 2. All of the y values are multiplied by 2. And then we have our h value of positive 4. That shifts the graph 4 units to the right. So now we will add 4 to all the x values. In this step, the y values will not change. We're simply adding 4 to all the x values. And so these points we can put on our graph and then sketch our new one. 3, 2/3. 4, 2. 5, 6. 6 comma 18 and 7 comma 54. So because the graph didn't shift up or down, the asymptote hasn't changed. And there's our new graph. So if we state our characteristics again, our domain won't change. Our range won't change. Our horizontal asymptote remember, an asymptote is a line. It's an equation. It is the line y equals 0. So it has to have a variable, it has to have an equal sign. There is no x-intercept. Now the y-intercept, before we shifted the graph to the right, we had our y-intercept, but now that's changed. We can find our y-intercept algebraically. Remember, the y-intercept is always where x equals 0. So we can take the equation and set x equal to 0. So it'll be y equals 2 to the power, 2 times 3 to the power 0 minus 4. So that'll be 2 times 3 to the negative 4. So the 3 would move to the bottom to make the exponent positive, and 3 to the 4th is 81. So there's where our y-intercept is. It is the point 0 comma 2 over 81. And I said this before, there's often a question on the diploma exam where you have to find either the x or y-intercept for some function. And because if it's on a numerical response, or what wouldn't be a numerical response, probably a multiple choice question, the y-intercept might be in terms of some variable. Okay, so you might see something like the function is y equals, let's say a to the power, or a times b to the power x. When you let x equal 0 for that, to find the y-intercept, b to the 0 is 1. 1 times a is a. The y-intercept for that function would just be a. So that's more likely something that you would see, because if they just give you an equation, you can put it into your graphing calculator, graph it, and find the y-intercept that way. Right? So chances are, on a multiple choice, you wouldn't get a question like that with the function being all numerical. Better chance that it'll have some kind of a variable in it. So the answer is a variable as well. So again, we're doing a transformation of 3 to the x on the next page. So we'll start with that graph. Again, going through -1 comma a third. Zero comma 1, 1 comma 3, 2 comma 9, and 3 comma 27. So there's our base graph. So if we go through our parameters, the first one we see is that A is negative a half. So that's going to be 2 transformation. We're going to have a vertical stretch about the x-axis by a factor of a half, and also a reflection about the x-axis because A is negative. In this case, remember this is a transformation of y equals 3 to the x, so the base 3 is already there. We have a b parameter of 1/5, which is going to cause a horizontal stretch. And that is about the y-axis. And the stretch factor is always the reciprocal of b. So horizontal stretch by a factor of 5. And we have a k value of negative 5. So that's going to shift the graph down 5 units. Okay, so if we go through all of these parameters and write our new points after each one, first again being that A is negative a half. That's going to multiply all of the y values by negative 1/2. So 1/3 times negative 1/2 is negative 1/6. 1 times negative a half. 3 times negative a half. 9 times negative a half. Yeah, but I'm in the middle of a lesson right now, so when I'm done, I can get you set up. Can you work right through lunch? Okay, then we'll have to do it tomorrow. Okay. Our next parameter is our b value of 1/5. So we said that's a horizontal stretch about the y-axis, and the stretch factor is the reciprocal of b. So it's a horizontal stretch by 5. We're going to multiply all of the x values by 5. And lastly, we have our k value of negative 5, which shifts the graph down 5 units. So for this first point, because the y value is negative 1/6 and we want to subtract 5, we'll need a common denominator there, which would be 6. 5 with the denominator of 6 is 30 over 6. So negative 1/6 take away 30 over 6 would be negative 31 over 6. Negative a half, now we're again taking away 5. That'll be negative 10 halves. So that'll be negative 11 over 2 when we go negative 1 half, take away 10 halves. Negative 3 halves, take away 10 halves is negative 13 halves. Negative 9 halves, take away 10 halves is negative 19 halves. And negative 27 halves, take away 10 halves is negative 37 halves. So, first point is negative 5 comma negative 5 and 1/6. So negative 5 comma negative 5 and 1/6. Right there. The next one is 0 comma negative 5 and a half. Then 5 comma negative 6 and a half. Then 10 comma negative 9 and a half. And 15 comma negative 18 and a half. Because the graph shifted down 5 units, our horizontal asymptote shifted down 5 units. It would be at negative 5. Right, so the graph would look something like that. Again, we have arrows on both ends. So our domain hasn't changed. It's still from negative infinity to positive infinity. But our range definitely changed. We go from negative infinity up to negative 5, and again, neither is included, which we show by those rounded brackets. Our horizontal asymptote is the line y equals negative 5. This graph has no x-intercept. But our y-intercept does exist, and we actually have it in our table. Right? In our table, the y-intercept is where x is 0. That's the point 0 comma negative 11 halves. But remember, you can always find it by setting x to 0 and solving for y. If you were asked for the mapping notation for this, the parameters that affect x, if they are present, are your b and your h. Well, there is a b value here, a b value of a fifth, which we said was a horizontal stretch by 5. We multiplied all the x values by 5. And then all the y values are multiplied by negative a half first and then decreased by 5. It's your a and your k values that will affect those. And we can certainly use a graphing calculator. We can put this equation in the calculator, graph it, and then check the points on our graph, on our calculator, against the ones that we came up with in our table. So if you put that exponential function equation in the calculator, then we can see the graph and check the points that we got in our table to make sure that they are correct. So our equation is y equals, and I can use negative 0.5 because 1/2 is exactly 0.5. In brackets, I'll put a 3 to the power of, I'll use brackets again to keep my 1 over 5 together. 1 over 5x minus 5. I go zoom 6 to set my windows to their standard settings. And if I go into the trace mode, we can check these points that we generated. When x is negative 5, y is negative 5, and that 0.16 repeating is 1/6. So that point is correct. When x is 0, I get negative 5.5, which is negative 11/2. When x is 5, I get negative 6.5, which is negative 13/2. So all these points are being confirmed. Okay, so definitely use the graphing calculator to check. The graph that you get is correct. So we want to do a transformation here of y equals 4 to the x. Difference being here is that we are not given our initial table of values, so we're going to have to generate that. And just so I make sure I have enough room, I'm going to do it below here. So when x is negative 2, 4 to the negative 2 is 1 over 4 squared, or 1/16. When x is negative 1, 4 to the negative 1 is 1 over 4 to the positive 1, or 1/4. 4 to the 0 is 1. 4 to the 1 is 4. 4 squared is 16. When we look at our new equation, there is no a value, right? The original graph has a base of 4, so that hasn't changed. There is no coefficient in front of the 4, so there is no a value. But we have a b value of negative 2, an h value of negative 5, and a k value of negative 3. So those are the three transformations that we have to do. The first being, again, a b value of negative 2. Now, it did say to describe the transformation, so we should probably do that. B equals negative 2, so that's going to do two transformations. The first being a horizontal stretch, and that is about the y-axis. By a factor of 1/2. Remember, it's always the reciprocal of b, as well as a reflection about the y-axis. Then we have an h value, and remember, it's always the opposite of what it appears to be because the general form has x minus h. Here our h value is negative 5, which means it's going to shift 5 units left. And the k value of negative 3 means it's going to shift 3 down. So if we graph our base graph, negative 2, 1/16, -1, comma 1/4, 0, comma 1, 1, comma 4, and 2, comma 16, which we don't have room for, but it's going to be way up there. So this is our base graph that has the x-axis as an asymptote. So for b equal -2, that causes a horizontal stretch by a half and a reflection about the y-axis. So we can do those simultaneously by multiplying all the x values by -1/2. So all the x values by -1/2. So for this step, the y values don't change. Next, we have an h value of -5, which is going to shift the graph 5 to the left, or we'll subtract 5 from all the x values. So for that next point, 1/2 take away 5 would be 1/2 take away 10/2. -1/2 take away 10/2 is -11/2. And -1 take away 5 is -6. And then finally we have a k value of -3 that shifts the graph down 3 units. So we'll subtract 3 from all the y values. 1/16 take away 3. So 3 with the denominator of 16 I think is 48 over 16. So 1 take away 48 is -47 over 16. 1/4 take away 3 would be taking away 12/4. That's -11/4. +1 take away 3 is -2. +4 take away 3 is +1. And 16 take away 3 is +13. Because this graph shifted down 3 units, our horizontal asymptote will be at -3. So my first point is -4, comma, -49 over 16. So that's close to -3, just slightly above it. So I'm going to move this. So again, this is when x was -4. Y is slightly above -3. The next point we have is -9/2 or -4.5, comma, -2 3/4. So -4.5, slightly above the previous point. Then we have -5, -2. Then we have -5.5, comma, 1, +1. Yep. -5.5, comma, positive 1. So this graph has an x-intercept. And negative 6 comma 13, which is way up here. Okay, the graph would look something like that. So our domain never changes. These graphs will never have restrictions on x. Our range goes from negative 3 up to positive infinity. Neither are included. Our asymptote is a line y equals negative 3. If we look at our table, we don't have either intercept there in our table. So we're going to have to algebraically determine our intercepts. So our x-intercept is where y equals 0. So if we take the equation and let y equal 0, so you can certainly add 3 to both sides. But as of right now, you don't know how to get x by itself when it's up in an exponent, which means that you'd have to do this graphically on your calculator. In the next chapter, though, in chapter 8, this is going to be one of the applications of logarithms. Logarithms can be used to solve an exponential equation. So we're going to look at that in chapter 8. But for now, we'll have to do it algebraically. So you could start with the original equation and find the x-intercept there. So 4 to the power negative 2 bracket x plus 5, close the bracket, and then minus 3 on the end. We can find our x-intercept, which is our 0. It looks like it's between negative 1, 2, 3, 4. Looks like between negative 5 and negative 6, so second function trace. We want to find our 0. We'll put our left boundary at, let's say, negative 7. Our right boundary at, let's say, negative 4. And it looks like negative 5.396, but let's confirm that. All right, getting that x value back. Yep, negative 5.396 approximately. So x is at approximately negative 5.396. Find the y-intercept algebraically. We'll check it. So it's going to be at y equals 4 to the power negative 10, take away 3, which we can put in our calculator. So You might be tempted to round that to -3, but you can't because the horizontal asymptote is at -3. So you'd have to say approximately -2.9 repeating. And again, you can't say that it rounds to -3 because that is where the horizontal asymptote is. Okay? So we're going to see there are a lot of scenarios that can occur where the data will follow an exponential function. One example, a cup of water is heated to 100 degrees Celsius and then allowed to cool in a room that has an air temperature of 20 degrees Celsius. The temperature T in degrees Celsius is measured every minute as a function of time m in minutes. These points are plotted on a grid. It is found that the temperature of the water decreases exponentially at a rate of 25% every 5 minutes, and a smooth curve is drawn through the points, resulting in the graph shown. You're asked to write the equation of that transform function in that form. Y equals a times c to the power b bracket x minus h plus k. That can be used to model this situation. So this is again where we would follow that general formula that's on the formula sheet, a times b to the power t over p. And the first thing you need to realize is that b gives you the growth rate. Now in this case here, this is a decreasing function. Remember, for a decreasing function, the base is between 0 and 1. So it is found that the temperature decreases exponentially at a rate of 25% every 5 minutes. Your B value, your growth factor, though, isn't what it decreases by. Your growth factor is how much remains after each 5 minutes. So if it loses 25%, that means it maintains 75%. So our growth factor, which is what B is, will be 0.75. So we can put that in our equation. So now we have y equals a times 0.75 to the power t over p. Now we also know the graph tells us that the line y equals 20 is a horizontal asymptote. That is the temperature in the room. So the water will never get below that, and technically it'll never reach that either, because every 5 minutes the temperature is 75% of what it was the previous 5 minutes. And 75% of something will always be something. So again, because y equals 20 is a horizontal asymptote, that will be our k value. So we can now say y equals a times 0.75 to the power t over p plus 20. The next thing we can write in here is our p value. P is the growth period. In this case, that means how long did it take for the water temperature to decrease by 75% of what it was before. And we were told above that that happens every 5 minutes, right? It says that it is found that the temperature of the water decreases exponentially at a rate of 25% every 5 minutes. So our growth period, which is P, is 5 minutes. So now we can say that y equals a times 0.75 to the t over 5 plus 20. So now all we need to find is what a is, right? T is the same thing as x. That's our variable. That's going to be changing, right? You can find the temperature after 1 minute, after 12 minutes, after 15 minutes by changing t every time. That's our variable. We need to find out what a is, and we've done this before. We can take any point on the graph, and the only one we know for sure that is on there is the point 0, 100. So using the point 0, 100, we can say that 100 equals a times 0.75 to the power 0 over 5 plus 20. So now we can solve for a. Well, actually, let's subtract the 20 from both sides. So I'll give us 80 equals a times 0.75 to the power 0, because 0 divided by 5 is 0. And anything to the power 0 is 1. So a equals 1. Sorry, a equals 80. And so now we can write our equation. Our equation will be t equals 80 times 0.75 to the power t over 5 plus 20. Which again, we can check in our calculator. If we put this in there, to the power x over 5 plus 20. If we look at the graph on the page, it tells us what our windows should be. I'm going to go from, let's say, negative 10 on the x-axis up to, let's say, 120 with a scale of 20. And for y, I'll go from negative 10 up to 110. And again, a scale of 20. So it certainly looks like the graph that we have on the page. But we can check a few points here by going to the trace mode. If we let x equal 0, it starts at 100, which is correct. If we let x equal 20, the value of y is just below 50. So let's let x equal 20. There we go, 45.3125, below 50. If we let x equal 60, the value of y is just above 20. So it seems to work. Can't be 100% sure because we don't know the exact value of all these points, but seems that it is the correct graph. So therefore we have this correct equation. So radioactive element AM is used in household smoke detectors. The half-life is approximately 432 years. So what that means is that however much of this is in a smoke detector when it's produced, However much of that radioactive element, it takes 432 years for that amount to decay or disappear to half of what it started with. That's the half-life. Okay? So again, we want to write the equation of this function. So if we, again, start with this base function, remember we said that b was the growth rate. And in this case, it is a half, because the amount of the element is cut in half every 432 years. P, we said, was the growth period. How long it takes for the amount of the element to disappear to half of what it was before, that is 432 years. In this case, the x-axis is an asymptote, so there is no k value. So again, we can start to write our equation. Y equals a times b, which is a half, to the power t over 432. And once again, I can algebraically determine what a is by using a point on the graph, using the point 0, 200. So 200 will equal a times 1/2 to the power 0 over 432. And 0 divided by anything is 0. 1/2 to the 0, anything to the 0 is 1. So 200 will equal a times 1, or a equals 200. So now we can write our equation. It'll be y equals 200 times 1/2 to the power t over 432. And we could, if we wanted, put that equation in our calculator and check it against the graph that we have on our page, but it works. It is the correct graph. So how do each of the parameters relate to the transform graph? Well, the fact that we have an a value of 200 means that the graph was vertically stretched. About the x-axis, by a factor of 200. Now, the base 1/2 would already be there. Remember, that never changes. This would be a transformation of y equals 1/2 to the x. But what about the t over 432? So what you have to realize is that this is the same thing as 200 times 1/2 to the power 1 over 432 times t, or x. You see, if you make t a fraction by going t over 1 and you multiply top times top, bottom times bottom, you'll get t over 432. So that just shows us that in this case here, those two expressions are equivalent. But the second one that I wrote in black tells us that we have a b value of 1 over 432, which means that we have a horizontal stretch. And that stretch is always about the y-axis. By a factor of 432, the reciprocal of b. And you might be thinking, well, that seems like an awful lot of horizontal stretch, but look at the scale on the x-axis. goes up to 2,700 and beyond. That's a big number. Okay. So I'm going to put some questions on the board that you can work on. You definitely won't have to do all these, but I would just pick and choose a few from each section to work on. So that'll be questions 1 through 8 on those pages. So again, I would pick and choose some. You don't have to do them all, but you should do a few from each section just for practice.